Greetings. Welcome to Module 14, where we start Chapter 6, the last chapter for the course. And so we're changing completely of the topics that we've done in the last two chapters. And we're returning to look at another different way to solve second order equations. So this introduces the idea of integral transforms, which is a pretty important branch of mathematics, particularly in applied mathematics. So an integral transform is an operator T of the form where you take some function and it's some function of T and you transform it from the T domain. So example, that might be a time domain. For example, we're doing a mass spring system, and it moves it to another function that's working on an entirely different domain. Let's say an S domain, where it doesn't really matter what that domain is, because we never actually do anything there. So what we do is we take our function and we integrate it against some function k, which is a function of the old domain and the new domain. So it's a function of two variables. And so you integrate it over some part of the t domain, usually 0 to infinity or negative infinity to infinity or something like that. Now, the reason why you do this, of course, is because we're doing math, and so we like to change things if we can move from something hard into something simple. So the idea is that you can do something in this new domain, manipulate, get information, whatever, and then usually what you do is you then go back to the original domain by using the inverse of the transform. There's lots of different integral transforms. Probably the most famous is the Fourier transform. I think that was the first one. They're all useful in doing things like solving equations, or in applied math, they're really important in image analysis. For example, that's how CAT scans and MRIs work. Are really important in probability theory. And so there's lots of different transforms, and what makes it a particular type is the choice of that function k, which is either called the kernel or the nucleus of the transform. And it's not kernel in the abstract algebra sense of anything to do with identity. It's just kernel in the sense of being at the center, the nut, the seed of whatever's going on. Okay, so the first module question is a pretty straightforward one. Prove that the integral transform is a linear operator. That is, if you transform a linear combination of functions, then what you get is the linear combination of the transforms of the individual functions. That's for any function, f and g and numbers, alpha and beta there. Okay, so Laplace transforms, the ones that we're looking at. So this gives us a different way of solving initial value problems. A little technical point, it always assumes that your initial value problems are given at t equals 0. And of course, if it's not given at t equals 0, you've got to do some shift in the independent variable, do a horizontal shift to get it back to 0. So the question you're probably asking is, why are we doing this? It turns out they're really useful in the way they handle things like discontinuous forcing functions. So a typical kind of problem is you might have an electrical engineer, they have some system, some circuits or whatever, and what governs the circuits is going to be some differential equation. And you might have some discontinuous forcing function that you put in. Like, for example, you might put it in like a step function or whatever. Laplace transforms can handle that really easily. And in fact, using Laplace transforms, like if you have some unknown system, and if you put in kind of a few standard forcing functions and see what the response is, using Laplace transform, you can actually then use the outputs that you get from these standard functions to predict what will happen if you put in sort of any kind of forcing function. Okay, so that's kind of nice. And the trick why we're using Laplace transforms is it takes a differential equation and it turns it just into an algebraic equation. And so maybe algebra is easier to do than integration, which is how we solve differential equations. Okay, so technical details. So you see that we define an equal transform as some sort of integral, so we've got to worry about the integral converging. Okay, so we worry about piecewise continuous functions. So again, we're doing it on 0 infinity because we're always starting at 0 with our Laplace transform. So a function is piecewise continuous if it is continuous except at a finite number of points on any sub-interval of 0 to infinity. So there's allowed to be infinitely many discontinuities. There just can't be infinitely many in a finite interval. Like you can have a discontinuity at each integer point, that's okay. The other requirement is that the limits from the left and the right at any point exist. They don't have to equal each other. They don't have to equal the value of the function at that point. So you're allowed to have removable and jump discontinuities, if you remember those from calc, but you can't have asymptotes. You can't have infinite discontinuities. So for example, if we look at this function here, here's this piecewise defined as 1 minus t between 0 and 1, t minus 1 between 1 and 2, and 1 afterwards. It's actually continuous, right? Because it's kind of like a v. At the top end of the v, you just keep on going at 1. It's continuous, but its derivative is not, right? Because its derivative is minus 1, 1, 0. That's piecewise continuous, as is its derivative. So it doesn't matter that the derivative doesn't exist at the point 1 or 2. It's still a piecewise continuous function. Here I've got some kind of complicated piecewise defined function, which is equal to 0 between 0 and a half. It's then equal to a half between a half and 3/4. It's then equal to 3/4 between 3/4 and 7/8, and then equal to 7/8 between 7/8 and 15/16, etc. Okay, that is not piecewise continuous, right? Because in that interval between 0 and 1, you've got infinitely many discontinuities. So that disqualifies it. The other technical definition we need is the idea of exponential order. So a function is of exponential order if there exists constants m, a, and t, such that we can bound that function by an exponential function, me to the at, for all t past some point. So it's allowed to grow really quickly. Then as long as it settles down to just simple exponential growth, then it's of exponential order. For example, any polynomial is of exponential order, but e to the t squared is not of exponential order. right? Because e to the t squared to be less than some constant times e to the a t, we divide through by e to the t squared. That means we want m e, and then in brackets t times a minus t is always going to be greater than 1 for all t. But clearly at some point it's going to get a negative exponential, and the negative exponential goes to 0. So it's, in particular, it's going to get less than 1 on n. So that can't work. Okay, so if we have a piecewise continuous function of exponential order, the Laplace transform then is we take our function and we multiply it by e to the negative st, and then integrate that between 0 and infinity. And the fact that it's piecewise continuous and of exponential order means that that integral is going to converge. Okay, and in fact you can see that it's actually going to converge for more functions. For example, the function that I mentioned before, the like infinite little step function within this unit interval, that would have a Laplace transform. We're not going to worry about those. So we're going to use the convention that when I have a capital letter, that's going to be the last Laplace transform, and a lowercase letter is going to be the initial function. So the initial function is over some kind of time domain. What domain is S? Well, it's some kind of, I guess you would call it some abstract frequency domain. Kind of like if you did a Fourier transform, you would, the kernel would be e to the minus ist, right? And in that situation, the domain is a frequency domain because the Fourier transform picks up all the different frequencies of signals that you plug in. So, and somehow you can think of this as some kind of complex frequency domain, whatever that means. As I said, we're actually never going to do anything in that domain, so that's you don't have to worry about that. So here's some simple Laplace transforms. The Laplace transform of 1 is 1 on S, and the reason for that is pretty straightforward. You just integrate e to the minus st between 0 and infinity. Antiderivative of e to the minus st is e to the minus st divided by minus s. Remember, you're integrating against t between 0 and infinity. As t goes to infinity, the exponential outweighs the s on the bottom, and so that's 0. So you just get minus 1 on s, so you get 1 on s. Okay. If you were worrying about the domain, of course, you would have s being greater than 0. Even simpler is the Laplace transform of an exponential, right? Because when you put e to the at into the definition of the Laplace transform, then exponentials combine, so you get e to the minus s minus a times t. So you can take the antiderivative of that. You're dividing through by minus times s times minus a. And of course, we're talking about improper integrals. Whenever you've got an improper integral, when I write infinity as the bound, what I really mean, of course, the limit of that as t goes to infinity. And you get that the Laplace transform of e to the at is 1 over s minus a. And of course, s is bigger than a. Laplace transform of cos and sine. So you could do that integral. But the simplest way to do it is just to use Euler's formula, right? So we have plug in e to the ibt, okay? Then by what we did in number 2, then we know the Laplace transform is 1 over s minus bi. Okay, so we rationalize that by multiplying top and bottom by s plus bi, and we get that the real part is s over s squared plus b squared, and the imaginary part is b over s squared plus b squared. But when you went back to, originally when you look at e to the ibt by Euler's formula, e to the ibt is cos bt plus I sine bt. And so if you split that up into real and imaginary part, and you can then set that equal to the real and imaginary part of what we just computed, and then we can get 2 Laplace transforms for the price of 1. So easy. So here's just some examples. Laplace transform of e to 3t is 1 over s minus 3. Laplace transform of 2 plus cos t. So remember, Laplace transform is an integral transform, so it's linear. So it's going to be the Laplace transform of 2, which is 2 on s, plus the Laplace transform of cosine, which is s over s squared plus 1. And then we can just bring that under common denominators. You might ask, why am I doing that? Well, actually, really, you're going to be doing the inverse of that. So what's going to happen is you're going to be given some rational function, and then you're going to have to split it up. So you might remember that means partial fractions. And once you have it into its parts, you can then figure out what it was the Laplace transform of. Here's another one, 2e to the t minus 3 cosine t. Well, Laplace transform of 2e to the t is 2 over s minus 1. Laplace transform of 3 cosine t is 3s over s squared plus 1. And there I put it over common denominators as well. Here's a little trickier one. What's the Laplace transform of sine of 3t plus 2? You know, sometimes we have to do that, right? Because we might have some phase shifts. Well, we just use the addition formula for sine. So that's going to be sine of 3t times cosine of 2 plus cosine of 3t times sine of 2. And so we can take the Laplace transforms of that, and we get the answer that we see there. What's the Laplace transform of t? Well, we don't know. We have to do sort of first principles, which is to go to the definition of the Laplace transform. You see, we're integrating t times an exponential, so you want to do integration by parts. So we do the integration by parts. We get t e to the minus s t divided by minus s between 0 and infinity. Well, at both bounds, it's going to be 0, right? Because the limit as t goes to infinity of t times e to the minus t is 0. And when we plug in 0 into t e to the minus st, we get 0. And so we're left then with just the integral of e to the minus st divided by minus s. So we can pull out that 1 over s, and we get just a Laplace transform of 1. So it's going to be 1 on s times the Laplace transform of 1, which we know is 1 on s. So we get 1 on s squared. Okay, so your module question, second module question is, give me the Laplace transform of sine 5t plus t. Okay, so the big question is, what happens when we have a derivative? Okay, and what we see is that the Laplace transform of a derivative is s times the Laplace transform of the original function minus some number f of 0. Okay, so this is what happens when you take a derivative. Especially, basically, when you take a derivative, every time you take a derivative, you multiply by s. So you turn something differential into something algebraic, multiplying by s. And so the Laplace transform of the second derivative is what I've got there, s squared times Laplace transform of f minus s times f0. So that's a number times s minus f prime of 0. So of course you're getting f0 and f prime of 0 from the initial conditions. And you can use induction to get the Laplace transform of the nth derivative. And you can go backwards, right? So from number 1, if you let f of t be the integral of f, then what you see is when you're taking antiderivatives, you're dividing by s. So taking derivatives, you multiply by s. Taking antiderivatives, you divide by s. So the 2, 3, and 4 all follow from number 1, and number 1 comes from integration by parts, right? So Laplace transform of the derivative, okay, use parts. We get e to the minus st times ft between 0 and infinity, right? Because f is of exponential order, that's going to be 0. So you're going to have minus evaluated at 0. So that's where the minus f0 comes from. Minus, and by the parts, we're multiplying by s, right? And so that's why we get s times the Laplace transform of f. Okay, so that's where we're going from. So later on, next module, we're actually going to start looking at differential equations. So just at the moment, we're just seeing how to take a Laplace transform, and we see that when we take a differential equation, we're actually turning it into an algebraic expression. Okay.